Hi all, welcome to my YouTube channel Know About Embedded System. In today's video, I'll explain you how to develop an embedded C code for pulse width modulation. So in the previous video, we have discussed what is pulse width modulation, what is single edge and what is double edge PWM and what are the applications and how to generate the PWM signal. All these things we have discussed in the previous video. In today's video, I will teach you how to develop an embedded C code for pulse width. Before starting the video, if you are a new viewer to my channel, kindly subscribe to my YouTube channel and gain the knowledge on. Let us start the video here. So before going into the programming, we have to analyze or we have to understand how the physical circuits are designed in the microcontroller. As you know that guys already, I'll be using a LPC1768 microcontroller. I told you many times already, you can use any microcontroller. It's not an issue, but only the thing is according to the controller, we have to select the port pins and we have to understand the design. In this 1768 microcontroller, we have totally 6 outputs available with respect to one single PWM. One single PWM will have 6 outputs and we will call it as 6-channel PWM. In LPC1768 microcontroller, we have 6-channel PWM. We can generate 6 outputs at a time. 6 PWM, single edge PWM. You can generate, if you want to go for double edge, you can generate only 3. So that is what it says now. Now you can see the port pin numbers as well here. For P1 pulse width modulation 1.1, they have defined some port pin numbers, so on like that. But my interest, you can use any port pin, no problem, and any channel you can use, but I'll be using 1.2. You can use anything, but for my convenience, I'm taking 1.2, which is connected to 1.20 or 2.1 or 3.25. Any port pin you can select, but I'll be selecting 1.20. You can select any port pin, no problem. So I'll be developing a code for pulse width modulation, and that pulse width modulation output is defined or it is designed in a P1.20. So this port pin, it is defined. So this is the fundamental thing before going to the programming. And the second important thing before going to the programming is registers. So what are the different registers we're going to use to generate the PWM? So there are lots of registers out there, but out of that 5 to 6 important registers we're going to use to generate the PWM. The first is timer control register. So what is timer control register? This is very simple. This timer control register is used to enable and disable the counters of your pulse width modulation. So basically PWM is also an application of timer. Here also we will use timer concept, and we will also use similar registers what we have seen in the timer. Okay, so TCR we are going to use. It is used to enable and disable the counters. Then we're going to use PR. You know that what is a PR already. PR stands for prescaler register, which is used to step down your clock value. And then we have MCR here. MCR stands for match control register. This match control register is used to enable different functionalities of your match register, whether you want to generate interrupt, whether you want to stop, whether you want to start or stop or interrupt. Okay. Then we have MR0 especially. So important thing lies here, guys. MR0 and MRX. There are 2 types of MRs are there. So we have MR0 and we have MR1 to MR6. So MR0 will hold the total time duration or nothing but maximum duty cycle. The MR0 is going to hold total time duration, nothing but T on and T off. So this is going to hold the total time duration, nothing but total period of pulse width modulation. And second thing is MR1 to MR6. So we have 6 outputs are there, and we have 6 MRs are there. If for each channel there is a MR register, MR1 to MR6. So this is going to hold duty cycle. These registers will hold duty cycles of your pulse width modulation. Or you can say MR1 to MR6 will hold the time duration for on period. Okay. So MR0 will hold total time duration, and MR1 to MR6 they're going to define on time. Okay, these two are important with respect to configuration. And next one, PCR, that stands for pulse width modulation control register. So this is a timer control register, and This is a pulse width modulation control register, PWM control register. So this is used to enable and disable the pulse width modulation output. This is used to enable the outputs of respective PWM. How to do that I'll tell you later. And then we have a latch enabled register. Here you can see load enable or a latch enabled register. This is used to enable the new PWM value. It's very straightforward. This is going to enable the particular MR value. This register is used to enable the respective MR. How to do that we will see in the coding part. So these are all the registers we're going to use in the coding part. Okay, so all the things almost we have explained the timer block. So if you want to know this explanation for this, you can watch my previous video, timer programming. There I have explained, and I will update the link in the description box. I'll be updating the link in the description box. You can watch my previous timer videos. So important thing what with respect to PWM is we have to understand only one with respect to PWM registers PCR. PCR stands for pulse width modulation program control register. So here we have two important operations we have to control. One is whether you're going for single edge or double edge, or the second one is whether you want to enable which output you want to enable. There are two blocks or two configurations are there, so which are defined like this: bit number 2 to bit number 6 of your PCR. Okay, so when you configure the bits from 2 to 6 as a 1, try to understand here, when you configure bit number 2 to 6, when you configure 2 to 6, it is going to be configured as double edge, and when you configure bit number 2 to 6 as 0, then that is going to configure as single edge. Okay, so this is the one thing, and these bits you can see here, bit number 2, 3, 4, 5, these are all bits which are defined for single edge or double edge. So this is the one part of your control. Second part of the control is output enable. So to enable the output, bit number 9 to 14 of your PCR registers we are going to use. Bit number 9 to 14 are used to enable or disable PWM outputs. You can see here bit numbers we have mentioned: bit number 9, 10, 11, 12, 13 and 14. Okay. So now, so here whatever I'm highlighting, so I'm going to use channel number 2, which is defined with a bit number 2. So here I need to configure single edge or double edge, and to enable the output I need to use bit number 10. So when you use bit number 10, output will be enabled, and whenever you use bit number 2, you can configure as a single edge and double edge. Okay, so and then that much. And one more thing is that TCR, timer control register. This is similar to our timer only. Okay, so now let us this much only the register part. Let us go back to coding part. So in the coding, as you know that already, so most of the at least skeleton part of the code I have already written here. So here you can see I'm going to use P1.20. P1.20 I'll be using as pulse width modulation output. This is what I have written here, and also I have defined some macros related to pin function selection, and I have done clock configuration, and I need to develop two parts. One is a PWM configuration and PWM output generation. So two main thing I had to write it. Now you can see here line number 36. Line number 36 says that configure P1.20 as pulse width modulation 1.20. So I'm going to use P1.GPI P1.20 as pulse width modulation 1.2. This can be configured using our pin function selection, using our pin function block. Okay, so how to do that? If you want to know, you please watch my previous video, pin function selection. I'll update the link in the description box. Okay, so now let us come back to the main part of the pulse width modulation configuration here. So in the pulse width modulation configurations, the first thing is you can see I need to load a prescaler. The prescaler, it is similar to timer only. There is no difference here. Same thing we have to follow. Only the difference is I have to mention as a PWM here. Pulse width modulation 1 and then followed by PR. So PR is equal to 23 I had to load. So this is similar to our timer. So why we have to load 23? You please watch my timer video. In there I have explained why we have to load 23. So this is the first point I have to do it. The second point is I need to load total time period. So total time period is loaded in a MR0 register. MR0 stands for match register 0, and here I will be loading for 10 millisecond. 10 millisecond means 10,000 I have to load. Okay, so 10,000 I have to load for 10 millisecond. I am going to generate pulse width modulation for 10 millisecond. Then I need to enable it. If you want to enable that, I need to use LER register. So that stands for LER. So is equal to 1 left shift of 0. When I use the 1 left shift of 0, this is going to enable MR0. So just the right parameter is going to enable the respective MR. I'm using MR0. That's why I'm using a 0 here. Then I need to configure MCR here. MCR is equal to, in a interrupt mode I need to generate. Repeat mode, not in an interrupt mode. Configure MR0 in a repeat mode, similar to our timer configuration. Then I need to enable the output as a PCR. I need to configure PCR as a single edge. This is going to configure your output as a single edge. PWM 1.2 as a single edge. It's going to configure because this configuration is there. No? This is going to configure bit number 2 as 0. So this particular part is there. No? So this is going to be configured as 0. That's why 0 means single edge, 1 means double edge. Then I need to enable the output of 1.2, nothing but now I'm going to enable 1 left shift of 10. So this is going to enable the pulse width modulation 1.2 output, same register PCR. So here I'm doing single edge and here I'm doing enable output. Okay, and then finally I have to do one more configuration. TCR is equal to 1 left shift of 0 and then 1 left shift of 3 I have to use. So this is going to define, this is going to clear the pulse width modulation counter, then it is going to enable. So this is going to clear, this is going to enable, 1 left shift of 0 will enable and 1 left shift of 3 is going to clear the counters. So this is the function to configure your PWM. First part of the code to configure the pulse width modulation. Okay. So now the second part of the coding is I have to call the function. Here you can see I have already configured its prototype. Okay, and then I'm using a clock configuration, and then again I'm configuring the I'm calling the function call here. Now the second important thing here is, so we have to generate pulse width modulation output. To generate the pulse width modulation output, we have to use MR2. Okay, why we have to use MR2? I'm going to use 1.2 channel here. Pulse width modulation somewhere you can see here. I'm going to use a pulse width modulation 1.2. So that means second channel I'm using, and I need to use MR2 here. So MR2 is equal to 2500. So this is going to define pulse width modulation duty cycle. Simple formula. So on period divided by total time period. On period divided by total time T. Okay, what is the on period here? So on period, so this MR2 will define total on period. MR2 will define on period, total on period. So now 2500 is on period, and total time is defined with a 10,000. So if you do the calculation, you will get 0.25, nothing but 25% duty cycle. This is what I have explained in the theory part of your pulse width modulation. Please watch my pulse width modulation theory video. There I have explained what you mean by duty cycle. Okay, on time divided by total time T. Okay, the same thing we have to develop in the coding as well. So now I have defined here, and then I need to enable the MR value by using LER register. Now I'm going to use bit number 2 here, and then I'm going to provide small delay here. You can provide around 1000 delay just to generate and keep it for short term. So this is this much only the code, and I'll be generating few more cycles. So this is for 25%. The second one I'm going to generate 50%. Third one I'm going to generate 75%, and the fourth one finally I'm going to generate 95%. For 25% 2500, for 50% it is 5000, for 75% it is 7500, and finally for 9000, for 95% it is 9500. Only this much code, and I'll be keeping this complete in a while of one, so that it will be continuously, it is going to generate pulse width modulation 25, 50, 75 and 95. Okay, so this much coding. Now let us go back to the compilation process. I'll compile this code. Let us check for errors. So you can see there is no error here. Okay, no problem, there is no error. And I'll go to the debug window here. Go to debug window, and yeah, here you can see. So I kept it already logical analyzer. If it is not available, go here and open the logic analyzer. Click on that. Just run the code. So this is your PWM output. So now you can see it is running in a 95%. So this is your 95%, 25%, so this is 95%, this is your 25%, this is 50%, this is 75%, so this is 95%, this is 25%, 50%, 75%, and finally 95%. Okay, so in this way you can generate pulse width modulation with the help of coding or a double edge. So how do you configure pulse width modulation as a single edge or a double edge? Please write your answers in the comment section, and write your opinion in the comment section. So, and then if you feel this video is informative, please like the video and subscribe to my YouTube channel. Thank you for watching.